So we'll come to the next section, which is the contraction principle. And the contraction principle is really a major idea in analysis. It is very useful in a kind of surprising variety of applications. It both gives us an existence and uniqueness theorem, as well as a method of calculation, which may or may not be pragmatically useful, but it's there in principle at least. So I'd like to try to explain that to you. So the initial idea is just to look at a function from a metric space to a metric space. All right, and if that function has a point which just goes back to itself, then that's said to be a fixed point of phi. All right. So many equations can be viewed as fixed points for the appropriate maps. Existence of fixed points for certain maps implies existence for certain equations, of solutions for certain equations rather. And so this leads to the existence of solutions to differential equations, as well as the so-called inverse and implicit function theorems. All right. Now, of course, the inverse and implicit function theorems also tie into the Fouché derivative, as discussed in section 9, which I'm going to go really light on this semester because we're just kind of out of a little bit of time because of that snow day and stuff. Sorry about that. I always talk about the inverse and implicit function theorems in a little bit more detail in my advanced calculus class, so I'll probably leave it there. Anyway, get back on track here. If we have a mapping from a metric space X to a metric space X with metric D, then this function is said to be a contraction with contraction constant C if C is a number between 0 and 1 and the distance from phi of x to phi of y is less than or equal to C times the distance from x to y for all x and y and x. So this defines what we mean by a contraction map with contraction constant C. So the first order of business then is to see that if you do have a contraction map, something pretty neat happens. If you have a fixed point, all right, and you had another fixed point, suppose you had fixed point 1 and fixed point 2. If phi is a contraction, well, if we look at the distance from x1 to x2, that's going to be less than or equal to the distance from phi of x1 to phi of x2, right? Which is less than or equal to c times the distance from x1 to x2. So I didn't write all that down, but you know, this is the fact that its contraction implies this is less than that. Now, but if that's the case, that means 1 minus c times the distance from x minus x1 to x2 is less than or equal to 0. But since this isn't 0 and this is non-negative, that means that has to be 0. All right. So the distance from x1 to x2 is 0, which means that x1 is equal to x2. Voila! A contraction has at most one fixed point. Now, of course, the question is, does it have any? Right? Does a contraction have any fixed points? So if it has 2, it's only got 1. But does it even have 1? Can we prove that? Well, yes, we can. That's the contraction mapping theorem. The contraction mapping theorem says that a contraction mapping of a complete metric space has exactly one fixed point. I guess I should say we do need the complete metric space. All right. Although I will admit, at the moment, I have not thought about if I drop completeness, does this fail? But I would wager yes. But I'm not going to get distracted by that. Here we go. So we have a contraction map on a complete metric space. That means that there's some contraction constant C, such that the distance from phi of x to phi of y is less than or equal to c times the distance from x to y, right? And c is the number between 0 and 1. So, following Gamelin and Green and a host of others, we define recursively for m greater than or equal to 1, first of all, phi naught of x is x, all right? And phi m of x is phi m minus 1 of phi of x, okay? So the zeroth map is the identity, and right. Well, the first one is the given contraction map, and then past that, it's compositions of the contraction with the contraction with the contraction with the contraction. Now, he says, observe that the distance from phi m to phi m plus 1, both acting on x, is less than the c times the distance the m minus 1 and the mth composite of phi acting on x. Okay, that's just the, using the definition of contraction, and then again, right, and then again, until you get to that this is less than or equal to c to the power m, distance from x to phi of x. All right, that makes sense. Now, for 0 less than or equal to m, less than or equal to m plus k, we can similarly calculate that the distance from phi of m to phi m plus k of x is less than or equal to this sum. All right, I'll let you guys explain to me why we can do that. And then, so then using this up here, right, I can replace this with c to the power m phi of x, and so forth, c to the power m plus k, like that. At that point, you can factor out the distance from x to phi of x here. Right? Notice that if you factor out that distance, it would leave you like a cm plus 1 plus da da da. But it's probably worth noticing at this point that the sum 1 plus c squared plus da 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 plus ck plus so forth and so on, well, that's equal to, well, I mean, this isn't less than or equal to, this is just straight up equal to 1 over 1 minus c. If I truncate it, right, if I throw out, like, just kill off this piece, so it's just this finite bit, then it would actually be less than, or, I mean, okay, fine, it's equal if it's the full series, but it's less than if I omit terms in the tail of the series, right? All right, let me stop blathering on about obvious things. Now, the result then, putting this stuff together, is that the distance from phi m to phi m plus k of x is less than or equal to c to the power m over 1 minus c, the distance from x to phi of x. We will refer to this as 8.2, as does Gamelin and Green. Now, so as what happens as m goes to infinity, this is a number between 0 and 1, so that goes to 0, which means that, as m goes to infinity, this m and m plus k, likewise, if we take the limit as m and k going to infinity, well, then this goes to 0, because this goes to 0, which is to say that anyway, we can get that that's a Cauchy sequence. I believe it seems reasonable to me to say that the green thing implies that we have a Cauchy sequence. It's not directly that, fine, but it seems like a plausible jump. So we have a Cauchy sequence in X, and so it follows that since we're in a complete space, that there exists a limit point, xm of x converges to x star as it's a complete metric space. And so if we look at the distance from x star to phi of x, well, that's the limit as m goes to infinity of this. And all right, but then of course we can use the contraction property to get that. And then of course as m goes to infinity, this goes to x star. So that would, we can pull that inside and take that limit by continuity of the metric, I suppose, which we haven't proved, but you could prove. Anyway, so as m goes to infinity, this goes to x star, and then we have c, the distance from x star to x star, which of course is 0. But if this is less than or equal to 0, that implies that this is equal to 0, because that's not negative, which is to say what? Which is to say that x star is equal to phi of x star, which is to say that x star, the limit point, is in fact that fixed point we were looking for. And then by our previous proposition, we know that that's unique, right? So in summary, a contraction mapping of a complete metric space has exactly one fixed point. Related, if it's a contraction mapping, if you use a contraction mapping of a complete metric space with contraction constant c, and x star is the fixed point, then the distance between phi m of x and x star is less than or equal to cm over 1 minus c, the distance from x to phi of x. In other words, we have an estimate of how far we are from the fixed point for a given iterate, according to this estimate right here. Now, up next here in the red, he kind of sketches how we use this to solve problems. So, I'll go through it. I have something more specific to show you right after this, which might make more sense. I don't know. I mean, this is not bad. It's just I'm not going to go through the whole section here. So this is, in some sense, just to set up the last two nice examples that he has. But all right, focus here. So you have a linear transformation from a Banach space to a Banach space, and it's a bounded. The linear transformation is bounded by 1. Well, we can argue then distance t of x is the norm of that difference, which is this, which is that. And then, of course, if that's less than or 1, this is less than x minus y, which, of course, is the distance from x, y, a. So what we've just found is that the norm of t itself serves as a contraction constant for t. For t. So the norm t serves as a contraction constant for t. So then the question is, okay, great. If t is such an operator, then apparently, if x is a complete, if x is a Banach space, right? If it's a complete normed linear space, then we ought to be able to iterate to find the fixed point. So how do we find that fixed point, x star, such that t of x star equals to x star? Well, what they propose is that we consider solving x equals to u plus t of x, where u is given and x is at the moment unknown. And we let phi of x be u plus t of x. And so look at, here's a list of equivalent things. X star is a solution of the star equation, all right? If and only if, what does that mean? X star is equal to u plus t of x star, all right. But since I just defined phi of x to be that, this is really the same as saying phi of x star, which by the way is u of t of x star, is equal to x star. Right? So x star as a solution of star is to say that x star is a fixed point of phi. But guess what? Phi defined as, I'm looking for a, I guess this will have to do. So here's the definition. Phi right there, right? Ooh, man, this Sharpie's not been open for a while. It's very, very pungent. Yowzers. But phi so defined is in fact a contraction map with, again, contraction constant norm of t because of this little calculation right here. So the difference of phi, the u's cancel, then we get the difference of t at x and y, and so we're right back where we started again. At this point, they say, okay, so suppose x sub 0 is 0 and define x sub n plus 1 to be u plus t of xn. Right, I guess u is given here, and t is given, right? And so this is how we iterate. Well then, Theorem 8.2 says that if we calculate xm minus x star, well, that's going to be less than or equal to the norm of t to the m power times the norm of u divided by 1 minus norm t. In other words, this gives us an estimate of how close the mth iterate here in star star is to the thing we're looking for. So we can find x star by just iterating as given in star star here. And that's the deal. And now we actually looks at a couple of explicit examples of that in Gimlin and Green. I'm going to go back to some notes I have from advanced calculus concerning Newton's method and the contraction mapping for the remainder of this talk, because I think that might be useful to you guys to see. And you can read what remains in Gimlin and Green. Anyway, so here we go. This is, I think, based on Edwards' Advanced Calculus, which is the book I've used. I wouldn't be able to tell you exactly what page at the moment, but it's probably obvious if you look. So here's the problem. Suppose you want to solve f of x equals to 0 by guessing a point, right? So if you plug in x naught, and you get f of x not equal to 0, like, oh well. So what you can do is you replace f of x by its linearization and look for the 0 of the linearization. So, replace f of x by its tangent line at x naught, namely this. And then you can look for where this, linearization has a 0. That's going to be, you do the algebra. It gives you x1 is x naught minus the quotient of f of x naught divided by f prime of x naught. So, of course, we need the derivative to be non-zero in order to do this, but you can do that, and then that gives us the next best guess to see if f is 0, right? Now, of course, if we plug in f of x1 and we get 0, then we're done. But otherwise, we can use that new point x1 to find the the tangent, excuse me, the tangent approximation to f based at x1. And then we can look for the 0 of the tangent to f at x1, right? And call that x2. And ideally, this gives us a sort of a way of zooming in to the possible zeros to a function. This is the naive Newton's method, all right? I said naive, cumbersome Newton's method, all right. And so generally speaking, actually, it doesn't converge. There are various persnickety things that can happen. But I will next look at an example. Figure 3.2 and page 162 of Edwards to see some bad behavior. But let me go on here. So here's a refined version of it. If we have that the function changes sign from a to b, and if we have that the absolute value of the derivative is less than m, then so m is an upper bound on the values of the derivative. I think max slope is m is the way to say that. Max magnitude of slope is m. All right. Then you can define sort of modified Newton's method. Xn plus 1 is xn minus f of xn over m. All right. Or this if it's less than 0. And that will converge to x star where f of x star is 0. That's the claim. And the way that's proved is with the contraction mapping. And so I have another proof of the contraction mapping business here, but this is special. This argument is just for a contraction mapping from the closed interval to the closed interval. But this is a specialization of the thing we just proved. Although the proof here might be more complete, maybe we should look at it. So constant k less than 1 means that. So that says that the distance from phi of x to phi of y less than or equal to k times the distance from x to y, right? Because the distance function on the reals is just the absolute value of the difference. Anyway, theorem is that there's a unique point x star for phi if you have that condition. Moreover, if you have x naught as initial point in AB, then the sequence defined inductively by xn plus 1 is phi of xn converges to x star. And here's an estimate on its error. Xn minus x star is less than or equal to k to the n divided by 1 minus k times x naught minus x1. So this is the analog of theorem 8.2 for the case of the modified, well, for the case of a contraction mapping from the closed interval AB to the closed interval AB. As I said, amazing. So here's the proof. X that is that minus that, which, okay, so by the contraction, phi is a contraction mapping, right? So that's k times that difference, which is, k squared times that distance, because we keep using the, okay, so the next step here is that, okay, so you do that, but then this is phi of x minus 1, phi of x minus 2, right? And then use the contraction the contraction definition to bring out the k squared and replace it with just the inputs. And you keep doing this. Eventually you get to k to the n times x1 minus x naught. I say if 0 is less than n less than m, then adding 0 and applying the triangle inequality, we have xn minus xm is less than or equal to that. Alright. Ooh, which is, so this step right here, remember my previous one, I was like, I'll let you guys explain that. So here's the analog of the let you guys explain that step. It was triangle inequality and a bunch of adding zeros. I would wager the same was true for the thing I asked you guys the question where to come from. Anyway, so that minus that is can be rewritten as this is less than or equal to this sum. It's sort of like adding and subtracting xn plus 1 all the way out to xm minus 1, like so. Gives us this sum of differences, each of which can be replaced with k to the, this one is like, you know, k to the, goodness gracious, oh, n minus 1. So k to the n plus da 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 plus k to the m minus, yeah, k to the m minus 1 times that difference of the x1 and x naught. But then you can just replace that with the full geometric series, which of course becomes 1 over 1 minus k, like so. And that's the estimate, right? And see, moreover, let's see here. That's the estimate. As n, oh, I guess as n goes to infinity, this goes to 0, which is to say that xn goes to x star. So, right. What's left to prove then? Since phi is continuous, epsilon greater than 0, we can choose delta as epsilon over k. 0 less than x minus a less than delta, which means that phi of x minus phi of a bar is less than or equal to k times x minus a bar, which is less than k times epsilon over k, which is less than is equal to epsilon. Consequently, the limit as x goes to a bar of phi of x is phi of a bar. Oh, so I'm saying that the contraction condition implies continuity of phi. All right. So what's next here? Continuing. So, oh, and then if it's continuous, I can put the limit inside of phi, and the limit as n goes to infinity of phi of n is x star, which, well, the fact that the limit as n goes to infinity of xn is x star, well, I'm sorry, there's something I'm missing here. Oh, phi of xn, of course, is what? That's also xn plus 1, right? So xn plus 1 as n goes to infinity is x star. Because we already know from our previous work that, you know, this this right here as n goes to infinity, this clearly goes to 0, which means that xn goes to x star. And that's also true for xn plus 1, as would appear here, right? Because phi of this is xn plus 1 by construction of x of n. Therefore, x star is a fixed point, and here I give a separate, in this context argument, of the uniqueness of the fixed point. If you had 2 of them, you would get this, which then implies that they're equal. So the fixed point is unique. And then, of course, you still wonder, well, how does that support the max slope modified Newton's method? Well, that proof is still to come here. That is, if you have a function which switches signs from A to B, and the derivative is bounded between M and M. Actually, this may be an even better theorem than the one I had before. Given x naught in the equals interval A to B, we define the sequence by this, and that converges to a unique solution, unique root x star in AB of the equation f of x equals to 0. Well, I know that the root's unique because I've assumed that they've got no turning point. I made the slope go between M and M, which says that it can't turn around. So there can be, it's this function's by assumption increasing, so there's just 1, 0 going from A to B. But anyway, more than that, if you look at the iteration defined like that, the difference between the fixed point, the limit point of the iteration and the particular nth one you're at, it's less than or equal to f of x naught over m times 1 minus m over m to the n. That gives us an explicit estimate on how far the iteration is from the truth, which is pretty awesome. So here's the proof of that. Phi from A to B, show it's a contraction mapping. So let's see what I do. I differentiate this, and I get that the slope, actually, phi prime of x is less than or equal to 1 minus m over k, m over m, which I defined to be k. So, okay, so phi is non-decreasing, and since f of a is less than 0, that gives me this is less than that, is less than that. Which is that, and so anyway, this jibber jabber in here proves that given the data in this problem and phi defined by this, that phi is in fact a contraction mapping with constant absolute value 1 minus m over m. And once you believe that, that gives you theorem 1.2, I believe. So it's here continued. Let me assume. All right. We just proved phi is a contraction map. So then use the contraction mapping theorem that says that there exists a star such that this is equal to that. So if we have a fixed point of this map, that is to say that f of x star is 0, isn't it? Yep. These cancel. We just get f of x star over m with a minus and multiply both sides by minus m. F of x star is 0. And also xn plus 1 is phi of xn is that. And the error estimate becomes this, which when you work out the details gives us the precise estimate claimed in the theorem. And then you can use that to set up the inverse function theorem. You know, if you want to solve f of x equals to y for x, how do you do it? If x is close to a, then you can replace f with its linearization and solve that for x. And that will give you a first approximation to the inverse function. And if you're in the mood, you could iterate, and that sequence of functions would give you a better and better approximation to the inverse function, which perhaps will converge to the inverse function. In fact, it does. That's the theorem. If you have a function from the reals to the reals, continuously differentiable, f of a equals to b, the derivative at a is non-zero, and there's neighborhoods of a and b such that a given y star of v in a sequence, you can define the sequence xn defined inductively like so. Well, then that converges to a unique point x star in u such that f of x star is equal to y star. All right. And well, anyway, I think I've done enough here. But again, essentially, the argument is to show, to find a map, use the contraction mapping principle. you define phi like so, show it's a contraction mapping, and it ends up having contraction mapping a half, and so you're able to prove that converges to something, and this gives us an iterative method to calculate the inverse function locally. And so that's one of the beauties of Edwards' advanced calculus, is he does all of this for the reals, but then he goes on and bumps it up to making similar arguments for Rn, which could equally well be given for a normed linear space. But derivatives have to be replaced with Fauché derivatives, and so instead of being non-zero to point, you have to have like invertibility of the linear transformation, which is the Fauché derivative. But a lot of these things go through. If you look at Edwards' advanced calculus, he has statements of the inverse and implicit function theorem where he characterizes the existence of the implicit solution or the inverse function in terms of course, the requisite data for the Jacobian matrix or for the Fauché derivative, but also he gives a picture for how the answer, the desired implicit solution or inverse function, can be attained as the limit of a sequence of functions. Furthermore, given the right conditions, terms and conditions, you can maintain the needed continuity or continuous differentiability of the sequence of functions to the limit function to which the sequence converges. But anyway, I'm getting too far off track. Gamelin's not the right place to look at these things, but he does at least give you some picture of how the contraction mapping is used with the Picard iteration to prove the existence and uniqueness theorem for differential equations, as well as the Fredholm alternative, which I think is the sort of the gateway to that other example. But anyway, I have said, I think, more than enough about metric spaces and all these things. I just want you to be aware of the terms and try to do some of the homeworks. You don't have to do all of them. If you leave a few undone, it's not going to be the end of the world. So tomorrow I will dive straight into topology, and we'll be there for a while. So thanks, guys.